Well, it turns out it's so powerful, it might have just shattered our understanding of the universe.
Since its launch on December 25, 2021, aboard an Ariane 5 rocket, James Webb has exceeded all expectations. Despite initial doubts, this ambitious scientific project has become a game-changer in the field of space exploration. By harnessing the power of advanced technology, the premier observatory has opened up a new window into the depths of the universe. Its infrared eyes allow us to peer through the cosmic dust and gas that obscure visible light, providing researchers with unprecedented views of distant galaxies, nebulae, and even exoplanets. The clarity and detail of Webb's images have stunned both scientists and the general public alike.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
From inexplicably bright galaxies to life on alien planets, and even the potential demise of our standard model of the universe. Join us as we James Webb's most terrifying images ever seen in history that wept away many of our preconceptions about the early universe. We now live in a universe that is full of bright objects. On a clear night, one can see thousands of stars with the naked eye. These stars occupy merely a small nearby part of the Milky Way galaxy. Telescopes reveal a much vaster realm that shines with the light from billions of galaxies. According to our current understanding of cosmology, however, the universe was featureless and dark for a long stretch of its early history. The first stars did not appear until perhaps 100 million years after the Big Bang, and nearly a billion years passed before galaxies proliferated across the cosmos. Astronomers have long wondered, how did this dramatic transition from darkness to light come about? After decades of study, researchers have recently made great strides toward answering this question. Using sophisticated computer simulation techniques, cosmologists have devised models that show how the density fluctuations left over from the Big Bang could have evolved into the first stars. In addition, observations of distant quasars have allowed scientists to probe back in time and catch a glimpse of the final days of the cosmic dark ages. The current models indicate that the first stars were most likely quite massive and luminous, and that their formation was an epochal event that fundamentally changed the universe and its subsequent evolution. These stars altered the dynamics of the cosmos by heating and ionizing the surrounding gases. The earliest stars also produced and dispersed the first heavy elements, paving the way for the eventual formation of solar systems like our own. And the collapse of some of the first stars may have seeded the growth of supermassive black holes that formed in the hearts of galaxies and became the spectacular power sources of quasars. In short, the earliest stars made possible the emergence of the universe that we see today. Everything from galaxies and quasars to planets and people. But if all cosmic history is a book, unfortunately, not all the chapters are visible to us. The cosmic dark ages make up the bulk of the book's missing pages. Imagine reading Shakespeare's Hamlet and skipping some initial scenes. You would transition from someone whispering in the darkness on the battlements of a castle in Denmark to a prince seeing ghosts and stabbing at tapestries. What happened? This is the situation that astronomers are facing. We now possess an excellent description of how it all started. The Big Bang theory has successfully explained the features of our universe. Just a few numbers, called the cosmological parameters, can fully describe the universe's initial conditions. And decades of observations have confirmed with spectacular precision that cosmic history seems to have begun with a fiery expansion from a single, still mysterious primordial point. But a shadow fell across the universe as matter cooled from its early incandescence, and relatively simple initial conditions advanced into intricate complexity. This is the source of the rift in cosmic history, the darkness where astronomers wander. What's certain is that a few 100 million years after the Big Bang, a blink of an eye in cosmological terms, the Great Shadow began to lift. Enormous clouds of gas collapsed, and stars, perhaps hundreds of times heavier than our sun, sparked a light, beginning a photonic deluge that over eons illuminated the universe. In this brief cosmic period, all the protagonists of our story, including black holes and galaxies, started to peek through from behind the dark curtain of the cosmic stage. The first stars were mostly made of hydrogen and helium, the lightest elements of the periodic table, as heavier elements did not yet exist. As they shined, these stars and their subsequent kin transmuted those light elements into heavier carbon, nitrogen, oxygen, and other elements crucial to the universe as we know it today. These elements, these ashes from early stars, eventually formed everything we observe around us, you and me included. To fully appreciate this milestone in our chronicle of cosmic history, we must fill in the missing pages surrounding it. How did the first stars, black holes, and galaxies form? How big were they? How fast did they grow? And how was their evolution interconnected? How did the cosmic transition from simplicity to complexity lead to at least one world where curious creatures gaze up at the sky in wonder? Without such details from these few but fundamental chapters, our understanding of the universe and our place within it will be forever incomplete. This is the deepest, purest reason why astronomers are seeking sources farther and farther out. Fortunately, we are privileged to live in an era when telescopes of unprecedented power, like the James Webb Space Telescope, can aid us in this cosmic endeavor. Not long after coming online, James Webb immediately discovered a series of enormous universe-breaker galaxies, containing what seemed to be almost as many stars as the Milky Way, dating to just 300 million years after the Big Bang. The finding caused a stir in the astronomical world, with some scientists suggesting that it had put our current view of galaxy evolution, or even our understanding of the universe, into doubt. Besides throwing out seeds of potential new crises in astronomy, the telescope also cemented an old one, the Hubble tension. Put simply, the universe is expanding, but depending on where cosmologists look, it's doing so at different rates. In the past, the two best experiments to measure the expansion rate were the European Space Agency's Planck satellite, which gave a most likely expansion rate of 67 kilometers per second per megaparsec, and the Hubble Space Telescope, which studied pulsating stars called Cepheids and found a higher value of 73 kilometers per second per megaparsec. Cosmologists thought this tension might be down to uncertainty caused by Hubble not distinguishing between Cepheids and background stars, but the Webb telescope snuffed out that hope with a result of 74 kilometers per second per megaparsec. Since then, cosmology has lurched deeper into a crisis that could reveal new physics or even break the standard model. What might resolve it? More measurements by James Webb, of course. An equally puzzling discovery. In a first, the James Webb Telescope may have glimpsed a rare type of star that astronomers aren't even sure exists. These stellar objects, called dark stars, might not have been fueled not by nuclear fusion, but by the self-annihilation of dark matter, the invisible stuff that is thought to make up about 85% of the matter in the universe. The candidate stars seen by James Webb will need more evidence to be confirmed. But if they're real, the finding could change our story of how the first stars formed. What's more, note that there weren't just inexplicably large ancient galaxies on James Webb's list of discoveries, but whopping black holes too. The first, Sears 1019, had a mass 10 million times that of our Sun and was found by the James Webb Telescope just 570 million years after the Big Bang, making it the oldest black hole ever spotted at the time of its discovery in April 2023. We say at the time because James Webb didn't rest on its laurels. Earlier this year, the telescope discovered the oldest and most distant black hole ever seen to date. The black hole dwells in the ancient galaxy GNZ11, which is 13.4 billion light-years away, and is thus seen as it was just 400 million years after the Big Bang. The black hole itself is around 6 million times as massive as the Sun and seems to be feeding on matter from its surrounding galaxy 5 times more rapidly than the limit suggested is sustainable by current theories. And according to scientists, this discovery could be a giant step forward for black hole science, especially in understanding how supermassive black holes reached masses equivalent to millions of billions of times that of the Sun in the very early epochs of the universe. For decades, how these gigantic space-time ruptures swelled to such staggering scales so early on is an ongoing mystery. Astrophysicists are currently exploring options that include the black holes being formed from the rapid collapse of giant gas clouds, although they haven't ruled out that some may have been seeded by hypothesized primordial black holes, thought to be created moments after, and in some theories even before, the universe began. In another stunning observation, the James Webb Space Telescope has found more thousands of Milky Way lookalikes that shouldn't exist swarming across the early universe. Shaped like warped vinyls and sporting delicate spiral arms, the Milky Way doppelgangers were found by James Webb more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made an abundance of such fragile galaxies impossible. But Webb's finding revealed that the disk galaxies are 10 times more common in the early universe than astronomers previously thought. The strange discovery joins others made by James Webb that point to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. As study co-author Christopher Consolis, a professor of extragalactic astronomy at the University of Manchester, said in the statement, "Using the Hubble Space Telescope, we thought that disk galaxies were almost non-existent until the universe was about 6 billion years old. These new James Webb Space Telescope results push the time these Milky Way-like galaxies form to almost the beginning of the universe. This implies that most stars exist and form within these galaxies, which is changing our complete understanding of how galaxy formation occurs. Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. A quick note: our own existence in a disk galaxy means that astronomers usually assume they must have good conditions for sparking life. If that's the case, it's possible that life could have started earlier in the universe than first thought. However, not stopped there, James Webb's ultra-powerful eye has also revealed glimpses of completely new, unexplainable objects. After being trained on the Orion Nebula, the Webb telescope found 42 pairs of Jupiter-mass binary objects, or jumbios, Jupiter-sized planets drifting through space in pairs, some as far apart from each other as 390 times the distance between Earth and the Sun. The jumbos are too small to be stars, but as they bafflingly exist in pairs, they are unlikely to be rogue planets ejected from solar systems. Their discovery has alerted astronomers to a brand new formation mechanism for planets, or even for failed stars. Notably, while James Webb glimpsed deep space unlike ever before, it caused a stir in the whole scientific community as piercing through dust to find an ancient, ghostly galaxy. Look at this picture. It's a very blurry, highly dust-obscured resident of the cosmos whose name is only a string of numbers and letters. It even sits at a distance so far from Earth that it slips in and out of the watchful eyes of various telescopes. The image, captured by the powerful James Webb Space Telescope, spotlights galaxy AS-TECC 71. But what's striking here is that we're seeing AS-TECC 71 the way it was just 900 million years after the Big Bang. That's when the universe was turning on its very first stars, absolute eons before our solar system was born. The Webb's view of this galaxy as a hazy speck of light is a far cry from many other glorious images of galaxies and galaxy clusters in its repertoire. However, even this smudge holds important lessons for our understanding of the early universe. As study author Jed McKinney of the University of Texas at Austin said in a statement, "The fact that even something that extreme is barely visible in the most sensitive imaging from our newest telescope is so exciting to me. It's potentially telling us there's a whole population of galaxies that have been hiding from us." Elsewhere, James Webb has helped set yet another record. Using the James Webb Space Telescope, astronomers have discovered star clusters in the cosmic gems arc that existed just 460 million years after the Big Bang. This marks the first discovery of star clusters in an infant galaxy, seen as it was when the 13.8 billion-year-old universe was less than 500 million years old. The cosmic gems arc, initially discovered by the Hubble Space Telescope and officially designated SPT-0615-JD1, is a gravitationally lensed infant galaxy around 13.3 billion light-years from Earth. That means light from this galaxy, seen by James Webb, has been traveling to Earth for around 97% of the universe's lifetime. The international team of astronomers behind this discovery found 5 young massive star clusters in the cosmic gems arc. These clusters existed during a period when young galaxies were undergoing intense bursts of star formation and emitting huge amounts of ultraviolet light. This radiation may be responsible for triggering one of 2 major phases in the evolution of the universe, the epoch of cosmic ionization. As Angela Adamo of Stockholm University and the Oscar Klein Center in Sweden and team leader said in a statement, "The surprise and astonishment were incredible when we opened James Webb's images for the first time. We saw a little chain of bright dots mirrored from one side to the other. These cosmic gems are star clusters. Without James Webb, we would not have known we were looking at star clusters in such a young galaxy." And when pointing Webb's sights on a star cluster about 1,000 light-years from Earth, astronomers discovered some unusual objects. The smallest they've ever observed. The smallest of the new objects that we found is likely to be the least massive free-floating brown dwarf that has been observed to date, say Kevin Luhman, an astronomy professor at Pennsylvania State University who is the lead author of a study documenting the team's findings. Brown dwarfs are one of the most unusual objects in the universe. Many objects we can see in the cosmos are some form of nebula, planet, star, or black hole. But brown dwarfs don't fall into any of these categories. The best way to describe them is star-like. They're not large enough to qualify as a star, like our sun, and they're so large that astronomers won't categorize them as a planet. Another name scientists use for them is failed stars. This leaves brown dwarfs in an unusual in-between state that makes them especially interesting for scientists studying one of astronomy's most fundamental questions. One basic question you'll find in every astronomy textbook is, what are the smallest stars? That's what we're trying to answer. On the other hand, we all know that stars and galaxies aren't evenly spread throughout our universe. Instead, they're connected by an enormous cosmic web, a gigantic network of crisscrossing celestial superhighways paved with hydrogen gas and dark matter. Taking shape in the chaotic aftermath of the Big Bang, the web's tendrils formed as clumps from the roiling broth of the young universe. Where multiple strands of the web intersected, galaxies eventually formed. Insights into the structure of this web not only give us a glimpse of the chaotic particle interactions that led to a universe existing in the first place, so astronomers using James Webb were stunned when they spotted the earliest strand of this web ever seen, a gassy tendril made up of 10 closely packed galaxies spanning more than 3 million light-years in length. The filament formed when the universe was just 830 million years old and is partially wrapped around a bright black hole. By finding more, researchers hope to find answers as to how the very first galaxies formed. Another addition to the Webb telescope's long list of cosmic distance records was its discovery of the most distant gravitationally lensed object ever seen, an Einstein ring, produced by the warping of light from a distant galaxy around a mysteriously dense foreground galaxy. How distant, a mind-bending 21 billion light-years away, which, given the universe's 13.8 billion years of age, means that the light from the galaxy traveled almost twice that distance due to the cosmos's expansion. Besides making for a very pretty picture, distantly lensed light shows like this could help astronomers to understand the puzzling nature of dark matter, the unseen substance believed to make up 70% of the universe's matter. Notably, while focusing to unlock the secrets of deep space, the James Webb Space Telescope also is revolutionizing our understanding of our closest cosmic neighbors. With its powerful infrared instruments, sharp spatial resolution, and exquisite sensitivity, Webb is forever changing our view of our celestial backyard. It is helping scientists answer important questions about our solar system, including how was the solar system formed, and how has it changed over time? Where did the chemicals necessary for life on Earth, like water and carbon compounds, come from? What are the icy small bodies in the outer solar system made of? How are planets around other stars like planets in our solar system? Webb's extraordinarily sensitive spectroscopic instruments and state-of-the-art imaging capabilities enable analysis and mapping of solar system objects, atmospheres, and surfaces. This is critical for studying planets, dwarf planets, moons, comets, asteroids, and ring systems. However, because Webb cannot point toward the Sun, it cannot observe objects between it and the Sun such as Mercury, Venus, Earth, or Earth's moon. Despite these challenges, exciting early results prove that it is possible to study planets with Webb. The telescope captured images and spectra of Mars, which allow scientists to study short-term phenomena like dust storms, weather patterns, seasonal changes, and, in a single observation, processes that occur at different times during a Martian day. In addition to finding the speedy Jovian jet stream described, Webb's view of Jupiter includes many fascinating details, including auroras, hazes, and tiny moons. In addition to finding carbon on the surface of Jupiter's moon Europa that likely originated in its subsurface ocean. In the newest study, astronomers have used James Webb to find previously unseen structures and activity in Jupiter's atmosphere above the Great Red Spot. These odd features seem to be caused by powerful atmospheric gravity waves. The Great Red Spot is the largest storm in the solar system, twice as big as Earth, and is believed to have been raging for at least 300 years. The winds of the Great Red Spot rage at around 430 to 80 kilometers per hour, up to 3.5 times as fast as a tornado here on Earth. But despite the storm's age, size, and power, scientists had actually suspected that the atmosphere of Jupiter above the Great Red Spot wasn't all that interesting. However, these new observations delivered by James Webb's NIR SPEC instrument, which observed the massive Scarlet Storm in July 2022, show that this assumption couldn't have been more wrong. After all, Jupiter never ceases to surprise. The telescope also detected a shockingly large water vapor plume spewing from Saturn's moon Enceladus. For the first time, Webb is giving scientists a direct look at how the water gushing from the surface of Enceladus, first detected by the Cassini spacecraft, feeds the entire system of Saturn, including its rings. Using Webb's infrared vision to study the atmosphere of Saturn's moon Titan, the only moon in the solar system with a dense atmosphere, scientists detected clouds and observed airflow. For those who don't know, Titan is the only planetary body other than Earth that currently has rivers, lakes, and seas. However, unlike Earth, the liquid on Titan's surface is composed of hydrocarbons, including methane and ethane, not water. Put Titan aside, Webb's huge mirror and infrared sensitivity make it easier to see small, faint bodies such as Kuiper Belt objects, comets, asteroids, and centaurs. In the first demonstration of this capability, described in detail above, Webb captured the DART impact, NASA's inaugural attempt to move an asteroid in space. Webb enabled another long-sought scientific breakthrough, this time for solar system scientists studying the origins of Earth's abundant water. Using Webb's NIR spec or near-infrared spectrograph instrument, astronomers for the first time have confirmed gas, specifically water vapor, around a comet in the main asteroid belt. This indicates that water ice from the primordial solar system can be preserved in that region. However, the successful detection of water comes with a new puzzle. Unlike other comets, Comet 238P Reid had no detectable carbon dioxide. Scientists also used Webb to capture the shadows of starlight cast by the thin rings of Chariklo, a small icy body more than 2 billion miles beyond the orbit of Saturn. Only 250 kilometers, or a solid 51 times smaller than Earth in diameter, Chariklo is the largest of the known centaur population. Its rings orbit at a distance of about 400 kilometers from its center. Information gathered from these rings will allow astronomers to explore the ring's thickness, the sizes and colors of the ring particles, and more. Scientists hope to gain insight into why this small body even has rings at all, and perhaps detect new, fainter rings. Besides, remember that many different kinds of ice exist in the outer solar system, not just the familiar water ice. Other molecules besides water can form ices, such as nitrogen, methane, ammonia, and carbon dioxide. Webb excels in the study of ices in the solar system through the use of spectroscopy. Most often, it provides reflectance spectra, sunlight shining on an object and reflecting back, while the surface absorbs particular wavelengths of light. For ices in the outer solar system, it's not just the composition that matters, it's also the shape and structure. Different structures of ice, such as amorphous, crystalline, and irradiated, look different in spectra. The type can tell scientists about the temperature history of the object. In crystalline ice, the molecules are arranged in a highly regular pattern forming lattices, such as in typical water ice on Earth. With amorphous ice, the molecules are irregularly grouped. In the cold, primordial gas between stars and across the universe, amorphous ice is the most common form. This is why Webb's integral field units are especially important. With a spectrum in every pixel, scientists can map out the surface of an object. One good example is Jupiter's moon Europa. By looking at a map of the carbon dioxide on Europa, we can tell that the carbon originated in the oceans, because it is most abundant in a region where the terrain is quite new. Another example of the exquisite quality of Webb spectroscopy is the clear signature of crystalline ice revealed for the first time on Chariklo. Ground-based telescopes had hinted at this ice, but Webb saw the crystalline ice signature for the first time. Some of Webb's most intriguing discoveries involve searching for the building blocks of life beyond Earth. This search hinges on the accurate identification of chemical markers, such as water, carbon dioxide, and ammonia. These markers have strong infrared signatures that Webb can detect in the atmospheres and on the surfaces of planets, moons, and smaller bodies. And in a remarkable finding, James Webb has spotted the potential signs of life in alien farts on a Goldilocks water world 120 light-years away. The exoplanet it found, K2-18b, is a sub-Neptune planet, weighing in somewhere between the mass of Earth and Neptune, orbiting the habitable zone of a red dwarf star. After taking an atmospheric spectrum, the Supreme Space Observatory found it rich with hydrogen, methane, and carbon dioxide, all chemical markers of a hydrogen-rich Hycean world that is a prime contender for extraterrestrial life. More tantalizing still was the detection of dimethyl sulfide, a cabbage-smelling compound only known to be produced by microscopic algae in Earth's oceans. The researchers want to take more peeks at K2-18b and worlds like it to find further evidence for extraterrestrial life beyond our planet. James Webb has mostly revealed insight into how everything began, but what about our eventual demise? Fear not, or maybe fear away. Doom mongers. The James Webb Telescope had you covered this year with a spectacular light show from a dying star, a preview into the demise of our solar system. The donut-shaped ring nebula, also known as Messier 57 or M57, is a 2,200 light-years distant corpse of an exploded star, harboring at its center a tiny pinprick of a white dwarf that is the last remaining piece of the star's core. As it reached the end of its life, the star exploded outwards, hurling its innards far and wide to form what looks like a gigantic eye. The explosion likely obliterated or ejected any unfortunate planets in its way, a fate that will similarly befall our own solar system in 5 billion years' time. Interestingly, in one of its latest observations, the Webb telescope has found evidence of two giant asteroids slamming into each other in a nearby star system. The colossal collision ejected 100,000 times more dust than the impact that killed the dinosaurs. The violent impact occurred recently in Beta Pictoris, a star system located 63 light-years away in the constellation Pictoris. Beta Pictoris is a baby compared to our own solar system, having existed for only 20 million years compared with our system's venerable 4.5 billion years. It was first detected in 1983 by NASA's infrared astronomical satellite spacecraft and is thought to have formed from the shockwave of a nearby supernova. While the young star system currently contains at least 2 gas giant planets, it has no known rocky worlds like our own. But rocky inner planets may be in the process of forming, thanks to large dust-producing collisions like the one spotted by James Webb. The researchers behind the new findings said in a presentation at the 244th meeting of the American Astronomical Society in Madison, Wisconsin. Because it is still very young, the star system's circumstellar debris disk, the vast ring of gas and dust surrounding the star, is a significantly more violent place than our own, making it the perfect place for astronomers to study the tumultuous early years of planet-forming systems. The team added that their findings could offer a rare insight into the history of our own solar system. And when it comes to hunting for the explosive deaths of massive stars in the early universe, James Webb is quite the cosmic detective. This celestial Sherlock Holmes has found evidence of 80 new early supernovas in a patch of sky as wide as a grain of rice held at arm's length. Not only is this 10 times more supernovas than have been uncovered before in such early cosmic history, but the sample also includes the earliest and furthest supernova ever seen. It's one that exploded when the 13.8 billion-year-old universe was just 1.8 billion years old. Data from the James Webb Space Telescope Advanced Deep Extragalactic Survey, or JADES program, helped a team of scientists find this unprecedented clutch of supernovas, which further includes Type 1 ablasts that astronomers call standard candles and can use to measure cosmic distances. Prior to James Webb's commencing operations in the summer of 2022, only a handful of supernovas had been found dating back to when the universe was only 3.3 billion years old, equal to around 25% its current age. However, the JADES sample contains many supernovas that exploded even further back in the past. In fact, some erupted when the universe was less than 2 billion years old. On the other hand, it is worth note that while the James Webb's primary goal is to produce awesome science, and not just pretty pictures, sometimes the pretty pictures are the awesome science. Case in point, the stunning portrait of NGC 5068, a spiral galaxy sitting about 17 million light-years away. No ordinary galaxy, this one is spouting off new stars at a record pace. A team of astronomers was able to use multiple instruments on board the telescope to capture the galaxy in all its glory. The detailed images help astronomers understand the formation and evolution of stars, including solar systems like our own. It also makes for a fantastic cell phone wallpaper. And like all NASA images, it's publicly available, so help yourself. Besides, NASA's time machine also provided us new insights of a lush, highly detailed landscape, the iconic Pillars of Creation, where new stars are forming within dense clouds of gas and dust. The three-dimensional pillars look like majestic rock formations, but are far more permeable. These columns are made up of cool interstellar gas and dust that appear, at times, semi-transparent in near-infrared light. Webb's new view of the pillars of creation, which were first made famous when imaged by NASA's Hubble Space Telescope in 1995, will help researchers revamp their models of star formation by identifying far more precise counts of newly formed stars, along with the quantities of gas and dust in the region. Over time, they will begin to build a clearer understanding of how stars form and burst out of these dusty clouds over millions of years. Newly formed stars are the scene stealers in this image from Webb's NIRCam. These are the bright red orbs that typically have diffraction spikes and lie outside one of the dusty pillars. When knots with sufficient mass form within the pillars of gas and dust, they begin to collapse under their own gravity, slowly heat up, and eventually form new stars. What about those wavy lines that look like lava at the edges of some pillars? These are ejections from stars that are still forming within the gas and dust. Young stars periodically shoot out supersonic jets that collide with clouds of material, like these thick pillars. This sometimes also results in bow shocks, which can form wavy patterns like a boat does as it moves through water. The crimson glow comes from the energetic hydrogen molecules that result from jets and shocks. This is evident in the second and third pillars from the top. The NIRCam image is practically pulsing with their activity. These young stars are estimated to be only a few 100,000 years old. Elsewhere in space, the Supreme Observatory also has captured the sharpest infrared images to date of a zoomed-in portion of one of the most distinctive objects in our skies, the Horsehead Nebula. These observations show the top of the horse's mane or edge of this iconic nebula in a whole new light, capturing the region's complexity with unprecedented spatial resolution. Webb's new images show part of the sky in the constellation Orion, the Hunter, in the western side of a dense region known as the Orion B molecular cloud. Rising from turbulent waves of dust and gas is the Horsehead Nebula, otherwise known as Barnard 33, which resides roughly 1,300 light-years away. The nebula formed from a collapsing interstellar cloud of material and glows because it is illuminated by a nearby hot star. The gas clouds surrounding the Horsehead have already dissipated, but the jutting pillar is made of thick clumps of material and therefore is harder to erode. Astronomers estimate that the Horsehead has about 5 million years left before it too disintegrates. Webb's new view focuses on the illuminated edge of the top of the nebula's distinctive dust and gas structure, the Horsehead. Nebula is a well-known photodissociation region. In such a region, ultraviolet or UV light from young, massive stars creates a mostly neutral, warm area of gas and dust between the fully ionized gas surrounding the massive stars and the clouds in which they are born. This UV radiation strongly influences the chemistry of these regions and acts as a significant source of heat. Thanks to Webb's MIRI and NIRCam instruments, an international team of astronomers has revealed for the first time the small-scale structures of the illuminated edge of the Horsehead. As UV light evaporates the dust cloud, dust particles are swept out away from the cloud, carried with the heated gas. Webb has detected a network of thin features tracing this movement. The observations have also allowed astronomers to investigate how the dust blocks and emits light, and to better understand the multidimensional shape of the nebula. And in other jaw-dropping images from James Webb, supernova remnant Cassiopeia A or Cas A gleams look like a shiny round ornament ready to be placed in the perfect spot on a holiday tree. For long, Cas A is one of the most well-studied supernova remnants in all of the cosmos. Over the years, ground-based and space-based observatories, including NASA's Chandra X-ray Observatory, Hubble Space Telescope, and retired Spitzer Space Telescope, have assembled a multi-wavelength picture of the object's remnant. However, astronomers have now entered a new era in the study of Cas A. In April 2023, Webb's MIRI started this chapter, revealing new and unexpected features within the inner shell of the supernova remnant. Many of those features are invisible in the new NIRCam image, and astronomers are investigating why. Indeed, infrared light is invisible to our eyes, so image processors and scientists translate these wavelengths of light to visible colors. But in this newest image of Cas A, colors were assigned to different filters from NIRCam, and each of those colors hints at different activity occurring within the object. At first glance, the NIRCam image may appear less colorful than the MIRI image. However, this simply comes down to the wavelengths in which the material from the object is emitting its light. The most noticeable colors in Webb's newest image are clumps represented in bright orange and light pink that make up the inner shell of the supernova remnant. Webb's razor-sharp view can detect the tiniest knots of gas, comprised of sulfur, oxygen, argon, and neon from the star itself. Embedded in this gas is a mixture of dust and molecules, which will eventually become components of new stars and planetary systems. Some filaments of debris are too tiny to be resolved by even Webb, meaning they are comparable to or less than 10 billion miles across, around 100 astronomical units. In comparison, the entirety of Cas A spans 10 light-years across, or 60 trillion miles. In the words of Danny Milosavljevic of Purdue University, who leads the research team, with NIRCam's resolution, we can now see how the dying star absolutely shattered when it exploded, leaving filaments akin to tiny shards of glass behind. It's really unbelievable after all these years studying Cas A to now resolve those details, which are providing us with transformational insight into how this star exploded. After all, as you see, NASA's James Webb Space Telescope pushed all our expectations in a variety of ways. Beyond the stunning infrared images, what really has scientists excited are Webb's crisp spectra, the detailed information that can be gleaned from light by the telescope's spectroscopic instruments. Webb's spectra have confirmed the distances of some of the farthest galaxies ever observed, and have discovered the earliest, most distant supermassive black holes. They have identified the compositions of planet atmospheres, or lack thereof, with more detail than ever before, and have narrowed down what kinds of atmospheres may exist on rocky exoplanets for the first time. They also have revealed the chemical makeup of stellar nurseries and protoplanetary disks, detecting water, organic carbon containing molecules, and more. Already, Webb observations have resulted in hundreds of scientific papers answering long-standing questions and raising new ones to address with James Webb. The breadth of Webb science is also apparent in its observations of the region of space we are most familiar with, our own solar system. Faint rings of gas giants appear out of the darkness, dotted by moons, while in the background Webb shows distant galaxies. By comparing detections of water and other molecules in our solar system with those found in the disks of other, much younger planetary systems, Webb is helping to build up clues about our own origins, how Earth became the ideal place for life as we know it. But it's worth noting that Webb's science mission is just getting started. There's so much more to come. We can predict what sort of incremental progress will be made, and what present unknowns will be revealed by gaining this information that eludes us at present. But what we can't predict is what's out there that we presently don't have any clues about. We don't know what sorts of remarkable discoveries we'll be able to make, simply because we're looking at the universe as we never have before. That's, arguably, the most important piece of doing science, the ability to open up what we call discovery potential. We know some of what's out there, and that's led us to some excellent expectations for what we anticipate that we're going to find. But what about the things that are out there that we presently have no hints of? Until we look, we don't know. Perhaps the search was best summed up by Edwin Hubble, but his sentiments apply precisely to the Webb telescope as well. With increasing distance, our knowledge fades, and fades rapidly. Eventually, we reach the dim boundary, the utmost limits of our telescopes. There we measure shadows, and we search among ghostly errors of measurement for landmarks that are scarcely more substantial. The search will continue. Not until the empirical resources are exhausted need we pass on to the dreamy realms of speculation. The life of the James Webb Space Telescope promises to be an intriguing one, and lengthy. The observatory used very little fuel to maneuver itself into its exact target location, and that means there will be extra to allow the telescope to orient itself for far longer than anticipated. Space engineers have calculated James Webb's expected 10-year lifetime could be doubled. In many ways, that is very good news. We will be able to do a lot more science with it now. In early March, the Space Telescope Science Institute, or STSCI, has announced which astronomy proposals have been selected to be given time with the James Webb Space Telescope over the next 2 years. Beginning this July, and officially called Cycle 3, Webb's latest solicitation received a record-breaking 1,131 proposals, the most ever for any space telescope in history. Such immense interest is not surprising, especially since we've just witnessed a series of James Webb's incredible achievements. But with that popularity, there are winners and many more losers. Only 253 proposals were selected. And among the winners there is a wealth of exciting science, including surveys to look for the universe's first galaxies, studies of possibly life-harboring exoplanets, and, for the first time, an attempt to leverage James Webb's power to find exomoons, natural satellites orbiting worlds beyond the solar system. David Kipping of Columbia University has been banging the exomoon drum for many years. Having unsuccessfully proposed exomoon searches for every previous James Webb cycle, he had tempered his expectations about his latest hopeful attempt, which was why, when he glanced at his smartphone while teaching a class on February 29th, he was so surprised to see an email notification from STSCI. That email confirmed that Kipping's wildest dreams had come true. In Kipping's words, the Webb telescope is by far the most capable current observatory for finding and then confirming candidate exomoons. An exomoon program he had proposed, led by his graduate student Ben Cassese, also at Columbia, had been selected. Their program will look at a Jupiter-sized planet orbiting the star Kepler 167, about 1,100 light-years from Earth. The planet transits its star, crossing the star's face to cast a worldly shadow toward Earth about once every 1,000 days. The next transit will unfold on October 25th, when Cassese and Kipping will be looking with Webb's far-seeing infrared eye in search of telltale evidence for one or more accompanying exomoons, down to the size of Jupiter's own Ganymede or Callisto. The team had submitted 3 exomoon proposals, but this was its favorite. "We didn't have anything that was as good as this," Kipping says, owing to the size of the planet, its distance from the star, and the fact that it transits. "If the researchers find something, we will have proof that exoplanets can host moons, opening up a new realm of scientific inquiry. If they don't, that null result will help set important constraints on moon formation, and perhaps hint that the lunar-laden worlds of our system are a cosmic rarity rather than commonplace." Emily Pass of the Center for Astrophysics, Harvard, and Smithsonian also had an exomoon proposal selected, the only other James Webb's exomoon search approved by STSCI. Hers will examine 2 Earth-sized worlds around a red dwarf star, TOI 700, about 100 light-years away. The goal is to look for moons that are true analogs to the Earth-Moon system. Her study will also be an important data point for learning the likelihood of moons forming among a red dwarf star's worlds. Early analysis of the famous TRAPPIST-1 red dwarf system, which contains 7 Earth-sized planets, has already dampened that expectation. By analyzing existing James Webb data of one of the planets, TRAPPIST-1H, we could rule out a moon orbiting that planet that was larger than Earth's moon. Of course, TRAPPIST-1 is a system of immense scientific interest every James Webb's cycle. Ongoing studies of data gathered during previous cycles are working out if some of the planets in the star's notional habitable zone actually possess an atmosphere, and, thus, the possibility of liquid water on their surface. From there, future work might then use the Webb telescope to scour any of TRAPPIST-1's promising planets for signs of life. Natalie Allen of Johns Hopkins University will lead a program in Cycle 3 to study TRAPPIST-1e, one of the habitable zone planets, for signs of an atmosphere. Past efforts have been stymied by the planet's tempestuous host star, which continually belches out powerful flares that all too easily disrupt observations. So Allen and her colleagues will watch the moment 1e transits the star at the same time as the innermost planet, 1b, which is known to have no atmosphere. By simultaneously observing those dual overlapping transits, subtracting the star's activity, and discerning the existence of an atmosphere on 1e should become easier. The boost in sensitivity, in fact, might even allow James Webb to sniff out some of that world's chemistry. But a key step toward identifying any prospects of life involves parsing a planet's light into a rainbow-like spectrum of multiple wavelengths, or colors. In addition, as expected, much of James Webb's focus in Cycle 3 will be on studies of galaxies. Of the approximately 5,500 hours of observing time awarded in Cycle 3, about a third went to galaxies, with exoplanets close behind and other fields of astronomy, such as studies of objects in our solar system, taking the rest of the time. Already James Webb has upended our knowledge of the earliest galaxies in the universe. It has broken the record again and again for the most distant one known, a record that at present stands at just 290 million years after the Big Bang 13.8 billion years ago. Elsewhere, Jehan Kartaltepe of the Rochester Institute of Technology will lead a survey in Cycle 3 to significantly bolster the number of known high redshift galaxies, those in the earliest universe, with their light most stretched to the red end of the electromagnetic spectrum by the expanding cosmos. The researchers will do so by employing a novel technique. In the past, James Webb has found such galaxies via simple, quick photometry by looking for them by their comparative brightness at reddish wavelengths. More time-intensive spectroscopy can then be used to follow up on the best candidates to determine their true distance and age. Rather than continue this tedious two-step process, Kartaltepe will instead rely on a potentially more efficient approach called slitless spectroscopy, essentially allowing the telescope's spectroscopic capabilities to measure every object in an image at once. This could net about 3,000 high redshift galaxies from the first 750 million years of cosmic history. What's an immense increase? Rohan Naidu of the Massachusetts Institute of Technology will be tackling a similar topic in Cycle 3 by studying some of the particularly large and red galaxies that have surprisingly popped up in Webb's observations of the first billion or so years post-Big Bang. Called little red dots, they appear much brighter and more massive than theorists have expected galaxies at this epoch to be. The position that Naidu and his collaborators have argued for is that there's hidden phases of black hole growth that we didn't really see until now. Thus, his program will seek to settle the debate about little red dots once and for all. However, note that not all of Naidu's proposals to use the telescope were as successful, though, and many other astronomers missed out entirely. It's just so brutal. There's so many excellent proposals that don't go through. Grant Tremblay, an astronomer at the Center for Astrophysics, Charles, Harvard, and Smithsonian, was part of Webb's Telescope Allocation Committee, or TAC, a group of hundreds of scientists tasked by STSCI to pick winners and losers from the torrential flood of proposals. The TAC ranked each proposal on a 1 to 5 scale based on scoring for scientific merit and various other factors. But while some proposals clearly rise to the top for selection, others in a murkier middle ground can be picked seemingly by chance. Tremblay wonders if there might be a better way to allocate James Webb's truly precious time. What is the difference between a 2.8 ranked proposal and a 2.9, he says. I would love to try a random number generator on that vast middle ground. In our own solar system, Mike Brown of the California Institute of Technology will use JWST to study Saturn's icy moon Enceladus. He will be looking to work out the origin of plumes of water that erupt from the moon's poles. It's thought these plumes may originate from an ocean beneath the moon's icy surface, in which case they could carry molecular evidence of habitability and even life within that dark abyss that could be collected by spacecraft. But they may alternatively originate from within the icy crust itself, quelling exciting visions of such remote submarine sampling. Brown will watch with James Webb to see if the plumes are constant. If they are, that would point to an icy crust explanation. If they instead erupt in bursts, they more likely originate from the ocean, timed to the periodic bending and cracking of the overlying ice sheet. It should be pretty dead obvious. We need to know the answer to this question before we send anything. Michael Jang of the University of Chicago will use James Webb to study a peculiar type of planet, one orbiting not a regular star, but a pulsar, a rapidly spinning neutron star left behind by an explosive supernova. For the first time ever, he and his colleagues will attempt to study the atmosphere of such a planet, in this case, a gas giant orbiting the pulsar PSR J2322-265, some 750 light-years from Earth. The world orbits so near its host that its atmosphere might be escaping and accreting onto the pulsar. That may explain how pulsars such as this one, a so-called millisecond pulsar that spins thousands of times per minute, are able to rotate so fast. One possible answer is accreting material from a planet. And this is not the only cosmic mystery James Webb might solve in Cycle 3. Elena Gallo of the University of Michigan will use the telescope to study a galaxy in the distant universe that may contain a direct collapse black hole. These are hypothesized astrophysical products of Einstein's general theory of relativity, in which clouds of gas in the universe's first 250 million years collapsed not to form stars, but rather straight into black holes. Such objects may serve as seeds for the subsequent formation of supermassive black holes, the circa billion solar mass titans found at the centers of large galaxies, including our own Milky Way. The galaxy that Gallo will observe appears to harbor a black hole as massive as the galaxy itself. A black hole that becomes so massive so fast is a telltale sign of a direct collapse. However, it is worth note that not all James Webb's Cycle 3 proposals will actually use the telescope itself. Dana Kasim of the Southwest Research Institute in Texas will perform a laboratory experiment as part of Cycle 3 to try and solve the sulfur depletion problem. We know that sulfur is one of the 6 elements crucial to life, but its cosmic origins are somewhat mysterious. Without knowing such specifics, scientists can't accurately trace the pathway this life-giving element takes to reach embryonic worlds in nascent planetary systems. So, Kasim will shoot electrons into an ice analog we might expect to see in such clouds to learn what sulfur-bearing molecules are formed. That might give us a handle on the problem, and highlights that for the most sought-after telescope in history, even space is not the limit. However, notice that James Webb alone cannot address all of astronomers' and cosmologists' questions. In fact, it is instead unveiling fresh mysteries, each generating additional inquiries that require a new generation of observatories and observers to answer. A lack of follow-through on such follow-on work would effectively diminish, in the long term, the immense economic and scientific endeavor that led to building, launching, and operating James Webb in the first place. Thankfully, scientists and policymakers are attempting to plan for such things in the post-James Webb era, at a moment when there are already exciting signs of surprising scientific results. The current major X-ray telescopes, Chandra and XMM Newton, have both significantly degraded since being launched more than 20 years ago, and neither is sensitive enough to detect black holes smaller than about 1 million solar masses in the remote cosmic regions that James Webb is exploring. Without a more powerful state-of-the-art X-ray observatory, we may miss our chance to understand how black holes evolved in space and time, an enigma revealed by successive generations of humankind's best, most cherished space telescopes. This helps explain why many astronomers are now already looking beyond James Webb and its forecast 20-year lifetime to envision an ambitious series of new great observatories, each sensitive to a different type of light. Ideally, all would have to be launched in relatively rapid succession around the time Webb's mission ends, maximizing scientific return via their overlapping operational timeframes. The original Great Observatories program debuted in 1990 with NASA's launch of Hubble and included Chandra and 2 additional now-defunct space telescopes, the last of which was sent to orbit in 2003. As recommended in 2021 by the congressionally mandated Decadal Survey of U.S. astronomers, this plan calls for a trio of new space observatories. The first, now named the Habitable Worlds Observatory, would launch in the early 2040s to study potentially Earth-like exoplanets, and much, much more, in optical, ultraviolet, and infrared light. The other 2, one for X-rays, another for far infrared, could launch later that decade or in the 2050s. Together, they could create a profoundly informative, more colorful view of the universe, ushering in a new golden age of space-based astronomy about half a century after Hubble's launch. For example, the proposed X-ray observatory could detect growing black holes as small as 10,000 solar masses within the mysterious early galaxies seen by James Webb, a factor of 100 improvement over Chandra's capabilities. However, whether through wavering political support, unanticipated technological challenges, or merely the harsh realities of NASA's overloaded portfolio, there is a good chance these decadal plans will not proceed at their optimal speed. A slower pace of development and funding could result in longer lag times between launches for the 3 new great observatories, reducing the likelihood that they will operate concurrently, as well as their overall scientific return. According to one analysis, having all 3 facilities operational by 2045 would require doubling NASA's astrophysics budget through the remainder of the 2020s and into the 2030s. Currently, there's as much evidence for such an increase becoming a reality as there are X-ray photons from these faraway galaxies. None. Far from doubling down on funds, the administration's latest budget proposes an increase in spending of only 3% for NASA's astrophysics division in the 2024 fiscal year. With its successive multi-billion-dollar investments in James Webb, Hubble, and their telescopic kin, the U.S. and its international partners sparked an ongoing scientific revolution representing humankind's best hope of learning our deepest origins, context, and fate. Fulfilling that profound potential and maintaining leadership in space science demands strong, sustained support for the next generation of observatories. Otherwise, we may fail to fully answer not only the current set of open questions, but any new ones that arise in our epical quest for cosmic understanding. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.